calculus students. This video is continuing on our learning target continuity, and we are focusing on types of discontinuity. And in the previous video we learned about all the definitions and the types of discontinuities, and this video is focusing on examples that you might see on the quiz and the AP exam. So example 1 is just a graphical example, and you need to find all the discontinuities in the graph and then state what type each discontinuity is. So I'm going to let you draw this graph, and as you're drawing it, try to figure out, because as you're drawing it you're going to have to lift up your pencil, right? Figure out how many different discontinuities there are. Okay, I'm assuming you've already drawn this, or I know you've already drawn this, and so let's just highlight where the discontinuities are. You'd have to pick up your pencil right there at that hole, right here at this jump, again at this hole, and then at this vertical asymptote. Okay, so just naming what each of these are. We have a removable discontinuity. I'll just say removable. Here we have a jump. Here, even though there's this little point down there, and some might think it's a jump because you like jump down to fill in the hole, because the limit from the left is equal to the limit from the right, this is a removable discontinuity. And then here we have a vertical asymptote, so this is an infinite discontinuity. Cool. So you might see a problem where you have to determine what type of discontinuity there is in a graph, but more likely you're going to have an equation and you have to figure out what the discontinuity is. Excuse me. So for holes and infinite discontinuities, the main thing is figuring out like where is the function undefined. And a function is undefined whenever you have whenever the denominator is equal to 0. I just like totally spaced out. So in this first part, A, I can't cancel out any of these terms. I'm kind of just stuck with what's in the denominator. So I can see, because of this term right here, the denominator equals 0 when x is 2. So I know that at x equals 2, there's going to be a vertical asymptote. So at x equals 2, that is an infinite discontinuity. Okay. So we also could have solved this by saying, alright, that's when x minus 2 equals 0, when the denominator equals 0, and then when we solve for that. That's how I got x equals 2, just in case you were confused. So you can always just set the denominator equal to 0. So in F, this should look a little bit familiar. It's like the problem from the warm-up. So you go ahead and factor this out and try to solve it as I do it and see if you can beat me to it. Okay? So hopefully you're looking down, not necessarily just copying what I'm doing. That. So I finished the problem, and you can look up and check your work with mine, or pause and try to finish it on your own. Because I can cancel out the terms x minus 1, I know that at x equals 1 is a removable discontinuity, and I know that at x equals 3 there is an infinite discontinuity. because that cannot be canceled out, so it causes a vertical asymptote. I just want to show you what that looks like visually. It's the same problem from the warm-up. So here's our equation, x minus 1 over x squared minus 4x plus 3. And you can see here is my hole at x equals 1. So the limit from the left and the right are equal to each other. We just have a little hole, which is a removable discontinuity. And then we have the vertical asymptote at x equals 3. Oh, and for part A, I actually do have, here's the graph in part A, and you can see there's my vertical asymptote at x equals 1, so an infinite discontinuity right there. Cool. Alright, and now let's look at this problem here. So this one is a little weird. Some people might be tempted to say, oh, we can remove, well, if some people might want to remove that and cancel it out, but because of the absolute value bars, we can't really do that. But we know where there could be discontinuity, just because of this problem. So thinking about what will make the denominator 0, that's at x equals 0. So I know at x equals 0, I might have a vertical asymptote, I might have some sort of hole, but if you don't know what this graph looks like, it's kind of hard to know what that might be. And so, if we're not sure what's happening there, let's take the limit. So we try to take the limit as x approaches 0 of f of x. The issue is that I can't plug in 0 and I can't cancel it out. So let's find the limit from the left and the right. Okay, so if you ever really don't know what to do, you can always just try to take the limit from the left and the right and see if they're equal to each other, see if it's going up to infinity or if it's approaching a number. So from the left, a number smaller than 0 would be negative 0.1. Put the absolute value over negative 0.1, so that gives me positive 0.1 over negative 0.1, which is negative 1. Okay, so I got a limit. And then from the right, let's choose a number slightly bigger, so that's the absolute value of positive 0.1 over 0.1, which equals positive 1. So this is a really special function where from the left, I could plug in anything to the left and I would just get negative 1 because it's the same number over the same number, but we have that negative sign. And then anything to the right of 0 would be the same number over the same number, which is 1. So because the limit from the left and the right are not equal to each other, but they're not going to infinity, so I don't have a vertical asymptote here, this is a jump. So f of x has a jump discontinuity at x equals 0. So when x equals 0, there's a jump. And I'll go back to Desmos so you can see this. Cool looking graph. It looks like that. That's it. So it's just two straight lines. The absolute value just really makes it kind of weird. It makes it not just a line at positive 1. Okay. Oops. Alright, and then we have one more example here. So we have this function g of x, and we're supposed to find the domain of g. So basically the domain are, that is all the x values that are continuous. So this is x values where the function is continuous. So any points of discontinuity, any holes or jumps, well, any holes or vertical asymptotes actually, will not be in the domain. Okay, so I'm going to say no holes or vertical asymptotes, right? So in this function g, we just have to figure out, are there any holes or vertical asymptotes? So let's factor this thing. You should try to be factoring it on your own, just to be practicing your factoring. Okay. Though I know I am lightning fast, because I've had lots of factoring practice. So once you factor, I see that there is a term we can cancel out or remove. We can remove that term, and then we're left with the other values. So I can see from here, oopsie daisies, from here, x equals -2 is a removable discontinuity. And then here, x equals -5 is an infinite discontinuity. Okay. Ooh, so that y was hideous. So at those values of x, the function doesn't exist. So since the function does not exist, it's not in the domain. There's no values there. There's a hole and there's a vertical asymptote. So, hole. This is a vertical asymptote. So because of those, there's no x values there. So I would say the domain is going to go from -infinity to -2, where there's a hole. And then it goes from -2 to oh no, whoops, I'm not going in the right order. I need to do the smallest one first. So since -5 is smaller than -2, I need to say that first. There we go. -infinity to -5, and then -5 to -2, and then -2 to infinity. There is my domain. And that is our final example, looking at discontinuities and how you might use them.